Morning, everyone. Welcome to session CMP214, High Performance Computing on AWS for Semiconductors and Healthcare Life Sciences. I am Srinivas Tadepalli from AWS, and I lead our worldwide go-to-market teams, which is basically our customer-facing teams for high-performance computing, quantum computing, and accelerated computing workflows. This morning, I have the distinct pleasure of being joined by two of our customers and guests, Mark from ARM and Sean from AstraZeneca. This is a high-level agenda in terms of what we'll be talking about for the next 40 minutes or so. So as you can see here, I'll kick off with what high-performance computing on AWS looks like, what our different customers across multiple industries are running and using the AWS services, how AWS has been innovating for the past 15 plus years, specifically to address the needs of HPC workloads. Mark will then talk about ARM's journey on AWS for their chip design and EDA workloads. Sean will then cover how AstraZeneca has been innovating on AWS for their healthcare and life sciences genomic workloads. And finally, we'll close it off with some closing remarks. So without any further ado, let's get started. So as you can see here, high-performance computing is really all around us. Whether if you take traditional modeling and simulation within the automotive and aerospace industries, where they're running product design, engineering, and simulation workloads, weather and climate. Many customers use AWS for running their numerical weather prediction as well as climate workloads. Many customers use AWS for healthcare life sciences workloads such as genome sequencing, cryo-electron microscopy, modeling and simulation. Semiconductor chip design for front-end, back-end, that's what Mark will talk about. Within the energy space, we have many customers running workloads such as seismic processing and reservoir simulation. Financial services is another key industry where we have many customers using AWS, so on and so forth. And one of the common things that we see across all these different workloads is a common set of patterns. And HPC workloads basically come in a variety of compute and throughput characteristics. What do those really mean? So some of these workloads is what we call as loosely coupled workloads. So these are basically embarrassingly parallel workloads where you're running a single simulation on maybe 2 or 4 cores, or maybe sometimes higher, but you're running tens of thousands, hundreds of thousands, or millions of them in parallel. Similarly, another classic HPC workload is what we call as tightly coupled workloads, where a great example for that is computational fluid dynamics or weather simulations, where you're running a single job on hundreds of thousands of cores using MPI and low latency networks in order to get the best price performance. More and more in the last 5+ years, we have started to see the emergence of accelerated computing workloads, which is mainly around large-scale machine learning and training workloads, where these workloads use special purpose GPUs and ASICs, and so on and so forth. And this is just a small snapshot of a variety of our customer base in terms of by industry, the types of workloads they are running. So you can see here, Sean will talk about AstraZeneca's journey within the healthcare life sciences industry. Similarly, within the energy space, we have customers like Commonwealth Fusions, who is a startup looking at nuclear fusion simulation, and they were here at re:Invent last year talking about their journey. Similarly, customers like Baker Hughes running modeling and simulation, so on and so forth. The other important aspect when it comes to running high-performance computing workloads on the cloud is the ability for our customers to scale and thereby achieve acceleration. These are 3 bespoke examples. The first one is within the healthcare life sciences industry. Dana-Farber Institute, they were actually here at re:Invent last year talking about their success. They were using the application called Virtual Flow, where they were able to scale to more than 5.7 million vCPUs in order to identify billions of cancer protein cells. Similarly, Woodside, another customer based out of Australia, they were able to use AWS for their seismic processing workload, which is basically identifying the natural gas below the subsurface. And they were able to compress the cycle time from 10 days to 90 minutes. That's 150x in terms of business acceleration. And finally, another customer of AWS, Descartes Labs, within the geospatial domain. Typically, at every year, we have the supercomputing conference where customers submit their LinPack results and get listed in the top 500. A geospatial startup, Descartes Labs, was able to use a credit card and spin up a close to 10 petaflop cluster on AWS and get into the top 50 a couple of years ago. So that's really the scale our customers are able to achieve by tapping into our HPC services. And as you can see here, AWS has been continuously investing and innovating within the high-performance computing and the accelerated computing domain for over a decade. And this is just a snapshot in the last 6 to 8 years. For example, one of our services, such as AWS Batch, and you'll hear a lot more about that in both ARM as well as AstraZeneca's journeys today. This was one of our first services for scale-out workloads. And all the way in the last 18 to 24 months, you can see there's been a lot of innovation, specifically around compute and storage and networking. Now, when it comes to running HPC workloads or accelerated computing workloads on AWS, we actually take a system-level view. What does that really mean? It basically boils down to 5 fundamental pillars: compute, storage, networking, job orchestration, as well as results visualization, right? So these are really the 5 pillars when it comes to HPC workloads. So let's spend a couple minutes on each of these buckets. So for example, within compute, that's EC2 stands for Elastic Cloud Compute. We have a variety of choices for our customers, more than 600 plus EC2 instances to virtually address the need of any kind of workload that you want to run. We have processors from Intel, AMD, NVIDIA, including our own silicon, the Graviton, for general purpose workloads. Plus, when it comes to accelerated computing, we also have Trainium and Inferentia. And when it comes to storage, customers have a variety of options to pick and choose, but for HPC workloads, these need high performance and fast I/O. So as a result, we have services such as FSx for Lustre, FSx for NetApp ONTAP, as well as OpenZFS, including many other services such as S3, EBS, EFS, so on and so forth. The third and most important service for HPC workloads is networking. Now, we have our own network called the EFA, stands for Elastic Fabric Adapter, and this provides a low latency, high bandwidth, high throughput network. On our GPU nodes, we have 3.2 terabits per second networking that these large-scale generative AI and ML workloads actually need in order to have those MPI communication calls across the nodes. And the fourth one is jobs orchestration, right? So you have your compute, storage, and network. Now, when you need to schedule and run your simulation workloads, you need some sort of a job scheduler, right? So AWS Batch is one of the oldest cloud-native schedulers on us, and that's super widely used by a variety of customers across a variety of workloads. We also have the AWS Parallel Cluster, and it actually supports Slurm as a scheduler within Parallel Cluster. And 2 weeks ago, we introduced a new service at Supercomputing Conference. It's called the Research and Engineering Studio that actually provides a portal for our customers to be able to submit their jobs through a simple web page. And finally, the last pillar for HPC workloads is visualization. So we have a service, namely DCV, stands for Desktop Cloud Visualization, that actually gives customers the ability to stream pixels over the network. Let's say you run a large-scale simulation workload that actually produces hundreds of terabytes or even up to petabytes of data. Instead of moving the data locally and then looking at the results or post-processing, DCV gives you the ability to stream pixels over the network instead of moving the data back and forth, right? So in summary, again, compute, storage, networking, orchestration, and visualization. These are the 5 pillars and all the services to address these pillars. Just in the last 15 to 18 months alone, we have launched 5 different types of EC2 instances. And you can see here, AWS has purpose-built compute for virtually all HPC workloads. For example, the first one is our HPC 7A instance. It's actually based on the AMD Genoa platform. It's got 192 physical cores, 768 gigabytes of system memory, so that gives you about 4 gigabytes per physical core, and 300 gigabit EFA, that's the low latency network. The other very interesting EC2 instance is our HPC 7G, which is actually based off the ARM64 processor. That's a great instance for a variety of workloads. Similarly, when customers are running data and memory-intensive applications, we have the HPC 6 ID instance. It's basically called the FAT node within the HPC community that actually provides up to a terabyte of system memory and 200 gigabit EFA and about 16 terabytes of local NVMe. So if you're running workloads that requires a lot of I/O to the disk, this is one of our recommended choices for our customers. We also announced our memory-optimized and high-frequency instances for some of our customers within the EDA space. It's based on the Intel Sapphire Rapids. And finally, within the GPU SKU, we have our P5 instance. This is the NVIDIA H100 GPU, purpose-built for large-scale ML training as well as HPC workloads. Let me take a moment to spend a couple of minutes on Graviton. As you have seen, our goal is to provide the broadest set of capabilities for our customers and choices when it comes to running their HPC workloads. And this is our latest innovation, our HPC 7G instance based on ARM64 processor. It's got 64 cores, 128 gigabytes of system memory, and 200 gigabit EFA. It's a great EC2 instance if you're running applications like computational fluid dynamics, numerical weather prediction, as well as computational chemistry codes such as Chromax and Amber and LAMMPS, so on and so forth. One of the interesting things that we have been doing, especially around the ARM ecosystem, is by working with a lot of our partners, the independent software vendor partners. So you can see here, this is a very small list of partners that we are working, but the list is quite exhaustive with the likes of Ansys and Cadence and Siemens and Synopsys, et cetera. And similarly, when it comes to the system integrator partners, we work very closely with the likes of Rescale and Ronin and Total CE and many others. So we understand that it is super important for us to also build collectively the ecosystem for customers to be able to use these instances for their HPC workloads. With that, let me now actually introduce Mark Galbraith from ARM, who will talk about ARM's journey on AWS for their HPC workloads.
Great. Thanks, Srinivas. Hi there. My name is Mark Galbraith. So I'm VP of Engineering for Productivity Engineering working for ARM. So I'm going to talk a little bit about our journey to the ARM cloud. And through that, I'm going to talk about, well, why use cloud and why use ARM servers in the cloud for EDA workloads. I'll give a few case studies, and then I'll talk a little bit about the benefits. So I'll just give you a bit more of an introduction to ARM before we get into that. So 70% of the world's population are using ARM processor technology. But we don't make chips ourselves, so we develop the IP and we develop the software to allow our partners to then build the SoCs and develop their software using our technology. 270 billion ARM-based chips have been shipped to date, with 30.6 billion of those in FY23 alone, which is quite incredible. And so if you think about the sort of products that you will see ARM coming in, is starting from the mobile revolution to the cloud disruption. So you're seeing ARM-based products in the infrastructure space, in, of course, the client space, automotive, and IoT. So whether it's your tablet or your cell phone, or it's servers in the cloud, or it's in your car, you'll find ARM technology everywhere. As has just been mentioned, AWS is an ARM IP customer through Annapurna Labs, and you can see where ARM servers have made their way into the AWS silicon over the last few years. Okay, so I also want to just mention sustainability as well. And so we've got a target by 2030 to reach net zero carbon. And so the chart on the right-hand side, you can see the yellow lines here are the targets that we've got. These are our target emissions. And the orange bars, they're actually what we've been able to achieve already. So an 87% improvement versus the baseline. And so how did we do that, and then how does that relate to cloud? So we started with using renewable energy for our offices and our non-cloud servers, so all of our on-prem. That's now 100% renewable. we have to work, of course, very closely with our supply chain, and then thinking about travel and looking at our carbon travel budgets and then implementing this into our travel policy. But of course, the usage of cloud has really been quite incredible as well. And the recent simulations that we've done, we see a 67.6% reduction in carbon emissions using the Graviton servers versus other non-Graviton technologies. So it's been really quite remarkable. Okay, so let me talk a little bit about the chip creation process. So we've got a little bit of a flow chart here. So everything from requirements all the way through design, verification, implementation, finally through to tape out and fabrication. And of course, making a chip costs multiple millions of dollars. So the design really has to be right first time. And this is the sort of exercise that chip design house such as Annapurna Labs is going to do. And so what ARM's providing to fit in with this process is we're going to provide the pre-validated IP units, so whether they're CPUs, GPUs, systems IP. So we provide them. We also provide the pre-validated cell libraries, the memory compilers, and ultimately this allows our partners to then take these pre-validated units and then build their SoC, and this is exactly the sort of thing that AWS through Annapurna Labs is doing. And when we think about those pre-verification steps that we're doing, this is where tens to hundreds of millions of CPU hours are then used in simulations to test those designs. And by ARM doing that up front, and whether it's, again, the soft IP, like our CPUs and GPUs, or even now with droplets, which are hardened versions of those, we're able to provide our partners with the quickest starting point for them to build their silicon. And therefore, with that huge compute target that we have, the usage of cloud has then become instrumental for us. So why move to the ARM cloud? So I really see it boiling down to three basic areas. And if I just take the first one, in terms of improving agility. So if you've got a fixed compute farm and you've got multiple projects all running at the same time, everyone's got their own milestones, it becomes like a game of Tetris to try and fit all of those project profiles into a fixed compute area. So by providing an elastic compute capacity, that allows you to run all those projects in parallel without disrupting any of them. And this leads to shortened development loops, which is incredible. And then we think about the project teams themselves. So this allows us to then unlock the efficiency. So what we find when we think about all the different workloads that we have when it comes to building a chip, we find that different compute is needed at different times. So sometimes it's a large memory machine that's needed. Sometimes sometimes you need multiple machines all at the same time. And so what this allows you to do is you get the right machine at the right number at the right time for your project teams. And this really allows them to maximize their productivity. And then also think about it as accelerating innovation. So in this case, this is where you can collaborate much more easily with all your project teams, whether they're within the same organization or with partners. And that can work extremely well. And it allows our teams to get to their quality milestones much more quickly, which leads to a much more improved time to market. So it helps tremendously. So we're going to deep dive a bit more into that design flow that was showing at the beginning and talk a little bit about the EDA tools that are then available. So looking at that overall flow, we split it into the front-end design, the back-end design, and then production and test. And so when we then think about all those different sections, and then think about our EDA partners, whether it's Synopsys, Cadence, Siemens, or Ansys, so they're providing technologies that are then available, now running on ARM servers that addresses every single part of the design flow. But more than that, when we think about the different characteristics of each of these workflows, so if you're running, so thinking about some of those front-end design tasks, so a large part of the IP verification process involves unit-level random simulations. And so they're typically quite short-running jobs. but you're running thousands and thousands of them in parallel. And so that maps really quite nicely into spot instances. And so we can then run them, and you can scale out very, very quickly. And then if we think about on the back-end design process, so this is where we're running along place and routes, or maybe static timing analysis. So these jobs run much, much longer. So there'll be many hours or even multiple days. And for these sorts of processes, often you're using, it could be a full chip database. The data sets are much larger. And so that involves typically a larger memory machines. The jobs run much for a longer time. And then you've got a lot more storage that you need to take into account there as well. So real different profiles when it comes to different stages of the design process. So then when we think about how to access cloud, so we've got a number of different ways of doing that. So I'll share with you a few examples just now. So one of the ways of doing it is we've developed some technology called Cloud Runner. And so this is a way where we containerize our workloads, and then it's these containers that we then take into AWS, and then we can then run them using AWS Batch. We can get access to the Spot fleet. We can get access to the on-demand servers. We also have the Cloud Bridge technology that we've developed, which allows our teams to directly access the AWS infrastructure. And then in that case, typically, we may be running AWS Batch, but also the usage of parallel cluster has been very useful for us. And the crucial thing here is our projects are, if you like, based on-prem, because we've still got all of our license servers and our project databases remain on-prem, but then we're essentially bursting into the cloud for all the extra capacity that we need. So I'm going to talk a little bit more about then how we run entire projects in the cloud. So before I do that, I'm going to talk a little bit about our on-premise environment. So I'll just do the build first. So effectively, what we have, our engineers will be using Exceed, and that's how they submit their jobs. As I said, you've got all your EDA tools, your license servers, your repositories are all based on-prem. We use an IBM LSF cluster, and then you can run all your jobs there, whether they're interactive or batch. And then when we decided to go into the cloud to run entire projects, then a different mechanism was needed, which is why we then developed our Cloud Foundation platform, which is essentially LSF on the cloud. So the front end looks almost exactly the same. Engineers still using Exceed, but then because we've built this LSF cluster effectively in AWS, that's where we then run our workloads. And so from an engineer's perspective, it's a very similar look and feel to how they operate on-prem, but now we're able to run in the cloud. And the important thing here is that instead of it being on-prem where the compute is there at all times, and that's, you're operating with that fixed size. In this case, you can extend and reduce as needed by the different workloads. Okay, so then thinking about, well, where are we now? So a couple of examples. So the chart on the left, so it's talking about our percentage of on-premise versus cloud. And so the blue is the cloud usage, and orange is on-prem. So you can see it increasing over the years. And so we're actually now at 73% of our compute workloads we're running in cloud. And so what we're finding is that all of our product groups are now using cloud daily as part of their development lifecycle. So whether you're a hardware developer or a software developer even, there's cloud going to be available for any of your workloads, whether it's simulation-based, formal workloads, place and route, or modeling. And so on the whole, we've been using Spot instances wherever we can for maximum cost efficiency. But of course, where we need to, we will use on-demand instances as well. And so with those, and also with those multiple platforms that we've been using with Cloud Runner, Cloud Bridge, and our Foundation platform, we're able to find the right platform that's needed for the right time. And there's a really sort of view, the process of getting into cloud, there's really sort of three main steps to it. The first part being enabling our teams to get into cloud, and then of course it's migrating them into cloud, and then the final stage is really then looking at that optimization piece, where you're mapping the best instance type for the given workload that you have, and really looking at the whole stack end to end, seeing how you can be most efficient. And then the chart on the right is really looking at our Graviton usage over time. And so this has been gradually increasing, and this is in part with the partnership they have with our EDA partners, and with them developing and optimizing their tools to run on ARM-based technology. And so we can see that continuing to increase over time. So thinking a little bit about the benefits now. So we've got the same workload on a couple of different tools. And so on the left-hand side with the first tool, so the green bars here are the Graviton instances, and the orange bars are the x86 instances. And so lower is better here, because we're looking at the cost to run an entire workload. And so the ARM's R7G is giving us the best overall cost. And then if we look at the lower charts on the bottom left, so this is the outright performance. And you can see here the performance is improving over time with the various generations of Graviton. And you can see that here we've got the Graviton and, in this case, the AMD instance are the two fastest ones. On the right-hand side, this, again, looking at different tool. This time, overall cost. Again, Graviton being the cheapest cost, and then comparable performance as well compared to the AMD instance. And so looking a little bit further ahead, I was going to talk about our primary cloud concept and vision. So we started off bursting into the cloud, and then we were starting to think about how do we run whole projects in the cloud. And now really, when we start to think about primary cloud, this is one cloud account for the majority of our work in our projects. And in this case, the whole environment is provisioned in a fully automated manner using code. So first of all, we set up this our virtual desktop infrastructure. And then from this area, we make sure that the data is co-located with this primary cloud. And then that allows us to set up in our primary cloud our foundation platform environment. But also we get access to, we can access partners such as Rescale with their technology. That then allows us to either go into on-premise. So when we run our project workloads, typically we can't run everything in cloud today because we've got some bespoke hardware that really has to remain on-prem. So these are typically board farms, FPGAs, emulators, that type of thing. And so having that technology allows us to then run workloads back on-premise. Now, whether it's our on-prem clusters, which will be getting more cloud-like in the future, or the bespoke hardware, it allows us to do this. But also allows us to access with our multi-cloud goals, we can access other cloud infrastructures as well. So to conclude, so design chips is very resource intensive and it is expensive, but AWS cloud helps us really improve productivity, reduce the costs, while decarbonising compute. So obviously, of course, we leverage AWS Graviton wherever we can for the better performance and the lower costs that brings. But then thinking about that sustainability angle. So the latest, as I said earlier, the latest Graviton simulations saw this 67.6 reduction in workload carbon intensity, which is really quite incredible. So of course, with cloud, we will find this optimal instance for the best price for the job at hand. And of course, we always have the scalability, which really improves the throughput for our project teams. And of course, when you give the teams what they need when they need it, you have happier engineers who end up being much more productive engineers. And as I said earlier, the EDA partners in our tools ecosystem is ready for ARM-based technology today, and ARM is now available in all our major clouds. So with that, I'm now going to hand over to Sean, who's going to tell us about AstraZeneca's journey to cloud.
Great, thank you, Mark. So I'm Sean O'Dell, and I work for AstraZeneca in the Center for Genomics Research. I'm currently working in Cambridge in the UK, and thank you for coming to this session so early in the morning. I know what you feel. I came from London last night, so thank you for coming so early today. We appreciate that. So what I'll talk about here today is to tell you, well, who are we? I'll talk about what we do and why do we want to get data into the hands of the scientist. I'll put this in context of scale, and we came up with this term petascale, but I'll explain what that means to us. And then I'll talk about how we do this with AWS to achieve outcomes across not only sharing data that we create, but also how does this relate back to the business and back to what AstraZeneca is trying to do. So the Center for Genomics Research, this started in 2017, and I've actually been working in this capacity or with the Center for Genomics Research in one way or another since 2018. And if we start at the value, so what is the value that we're trying to derive? Well, it's really around two things. You know, we talk about life sciences and we talk about healthcare. And in the area of science, or in the area of life science, we want to use information about your DNA or about your genome to help us drive better understanding of the biology of disease. And then in regards to healthcare, by using this information that comes from your DNA or from your genome across a large population of people, we can then derive statistically valid information, which will then help us to select patients for like new clinical trials, but also to influence the type of therapeutics that might be applied to a patient that has a condition. And we also refer to this in the industry or in this area as precision medicine. So we're trying to couple information that we have about your genome and analyzing that across a huge and vast set of data to then personalize medicine and selection of therapy to a person based on that information. So that is the value that we are driving or attempting to drive from the Center for Genomics Research. And to do that, we need different capabilities, or we need a set of capabilities. And the capability that is in the middle there that I'll probably be spending most of the time on, and my role is building these informatics and analytics pipelines and capabilities. So I'm going to talk mostly today about a platform built on AWS that drives us to being able to deliver these values to the business. And I'll give you some examples of what those outcomes are and also how we do that with AWS. But this is who CGR is. I work in informatics, which is the head with the gears in the slide there. And that's where my focus is, and that's what we'll kind of focus on today. Okay, so how does this all start when we think about data? And I said we want to get data into the hands of the scientists. So if you saw me in the elevator and you said, Sean, what do you do? I would say my job and the team that I'm on, our job is to get data into the hands of scientists so we can drive that value. So this is how it starts. We start on where we talk about sequencing, and this is going from biology, like blood or saliva, that comes from a person. So we are focused on humans, as not opposed to aliens, but on humans as opposed to like mice or something else. And what happens is people contribute, their biology, or their blood, or their saliva to what we call a biobank, for example. And there's some large biobanks that we work with. There's the UK biobank. There's a big biobank we work with in Mexico City. Mexico City population, that's the name of the project. And these are very large biobanks, like the UK biobank. 500,000 people have contributed what we call a sample into this biobank. So that sequencing step, what it does there is it takes that biology and it unravels that, and it creates bits and bytes. So now at this point we have files, or we have data. And then what we need to do is we need to extract and transform and load that data into places, repositories, that then people and scientists can run analysis or run analytics to drive discoveries or to drive innovation that then influences those values that we talked about. And it's really interesting when you look at our workload or our workflow here, because Mark has a very similar workflow. And I think one of the points that I think Mark has made, and then I will make as well, is that what we've talked about here, you can apply it, because I'm assuming you're not all in healthcare here today, but you can apply it to anything. So we call it the Genomic Workflow Orchestrator and the Genomics File Store, but you can think of it as the widget workflow orchestrator or the widget file store. And I think what Mark showed in his slides is it's almost exactly the same type of slide. So we have these steps that we need to run to get data from the sequencing machine as it comes off into what we call tertiary ingestion or tertiary analysis. So these are all workflows that we need to run, and that's what the workflow orchestrator does. So it coordinates and it orchestrates running all of these workflows in an automated manner. But we also need to keep track of all the data that's being produced by these workflows. And we refer to that as the genomic file store. And each one of these workflows, primary validation or ingestion, they're all reading data from the genomics file store and writing data back to the genomics file store. And when we started this project, we actually built the genomics file store, was the first thing that we built. And what is that? It's S3 objects, and it's also metadata about those objects. Because it's very critical that we understand how was this file created? What were the tools that were used to create all of this data? Okay? So this is our extract transform workload. It's ETL. It's really what it's all about. Has a fancy name, but it's about ETL. And when we talk then about the scale and the challenge, you know, we came up with this term petascale. We could say large scale or big scale, but petascale kind of refers to the fact that we're moving petabytes of data in and through these pipelines, and also storing petabytes of data in our genomics file store. Okay, and we have, I mentioned here, 25 petabytes of data. That's not necessarily what we're consuming in S3, but that is all the data that has kind of passed through this pipeline at various stages. All right? And we also need to have standardized pipeline. And Paula and I were speaking about this earlier, that, you know, I talked about 500,000 samples, but we have to process the first sample in exactly the same way as we process the 500,000 sample. So you need to have standardized pipelines, and you need to have standardized workflows. And of course, wrapping around this, we use, to make sure we do that, and to make sure we do that with code, and make sure we're testing that always in the same way. Of course, as you would expect, we use code pipeline, we use data lake, AWS data lakes to bring all of this data together into a place where scientists can access it. And we also, as part of our processing that we do, we use software called Dragon, which runs on F1 or FPGA instances. And there aren't thousands and thousands of those. So we also built our pipelines so it would be geo-distributed so that we can, in an automated manner, we can run our pipelines in, we use 3 regions, London, Dublin, and USC. So those are the things that you need to consider when you're building something like this. And in the genomics world, the claim to fame is, well, how fast can you do this? How many samples can you get through in a day? And using AWS and using the kind of technology that AWS provides, as Mark also mentioned, where you can burst and you can have large spikes of workloads, that is what has enabled us to get to this point where we can run some of these numbers. Like 38,000 whole exomes in a day is quite industry leading. We talk about whole genomes, 11,000 per day. But the point of this is that using AWS allows us to run at this scale. We call it petascale. You can use that term if you want as well. So here's some of the components that we use these are kind of the bedrock components, and Srinivas has talked about some of these. But this is the components that we use, kind of the core components. And they are as what you would expect. We use AWS Batch. AWS Batch is really our workhorse. I mean, we've been using it, as I mentioned here, we've been running in production since 2028. And AWS Batch, all those workflows that I was showing you in the previous slide, those are all running in AWS Batch. And each sample needs to run probably 10 batch jobs. So if we had 500,000 samples, that's a lot of batch jobs that run. But we also use AWS Parallel Cluster because Parallel Cluster has a nice interface that people are familiar with that have used HPC, has Slurm. And there are times that we burst from our on-premise Slurm cluster into AWS using Parallel Cluster, and that works quite well. And then to coordinate all this work, we use AWS step functions, and of course we use Aurora for database and Dynamo. And then S3, as I mentioned, is where we store all of our objects. We are using a new feature of S3 called Mount S3. I think it's called Mount Point S3. Mount S3 is the command. But that's really a handy feature now that allows you to mount an S3 bucket as it were a file system. And it does, I mean, there's been things that could do that for a while, but this is something fully supported by AWS, and we've been an early adopter of this and have been quite successful using that. Okay. So how do we stitch all this together? I know this is a little bit of eye chart, and I won't go through every box here. But this is how we automate all this. So when a person, there's an end user terminal there, an end user doesn't think about, oh, I need to run this on batch, and then I need to store the data in S3, or I need to load the data into a database. What an end user thinks about, and this is what we call a pipeline manager, thinks about is I have, for example, 500,000 samples that I need to get through my workflow, and I don't care how that runs. I don't even care if I'm a pipeline manager if that runs on AWS, to be honest, or it could run in Google. So that's how a pipeline manager thinks, and they just run a few commands to submit a processing set, a data set, for example, for 500,000 samples. And then we do what you would expect. This is not, I don't think what I'm showing here on the screen is really innovation. It's a standard core pattern that anyone can use. And it's your typical pattern of a job goes to a queue, that's dispatched by a Lambda function that then starts a step function that coordinates the work of running the batch job, collecting the data after the batch job finishes, keeping track of that data, storing that data in the metadata catalog, and so forth. But this is a very common pattern, and I think in the terms of kind of these types of diagrams that we see, this is a fairly simple pattern. And the point that I wanted to make to you, to leave you on this slide, is that anyone can do this, so this isn't related to genomics. This is, if you're processing widgets, then you could use this same type of pattern. Okay, so some of the outcomes I'll talk about. I mean, this is, well, what does this really mean? I mean, so what? So you ran these ETL jobs, and what kind of impact do they have? I think one of the things that I wanted to mention here that Mark and Srinivas also mentioned is that when we run, like, for example, billions of statistical tests, these are perfect examples of scatter and gather jobs. So we do that all running on AWS Spot, and it's quite on EC2 Spot. It's quite cost efficient to do that. But being able to do this and to run these billions of statistical tests, this does give us a value to our business because we can do it quickly, and we can get data into the hands of scientists quickly. We also then have been able to identify novel targets for medicines, and also has had a big impact on clinical trials. So now we can use this information that we've created and analyzed to target people for clinical trials, to get medicine into the hands of those people that has a basis of not only their clinical data, but their genomic data, okay? And we also, it's very important to AstraZeneca and many of the companies here, it's not just AstraZeneca, but to return what we've gained from being able to do this back to the scientific community. And we do that by publishing papers, as is the practice. So we want to make sure we're contributing back to the community. And I just have one example here. We call it the FEWAS portal. But what this is doing, that kind of tying this back together, is we're showing the linkage between a clinical observation, and I know that the writing is hard to read, but you can even reproduce this diagram yourself. But we're showing the linkage between clinical observation, in this case breast cancer, to genes that are in the yellow box there that have some type of linkage between this clinical condition. And this isn't a new discovery. I'm not sharing some secret that we just came up with, but this information, as a scientist, as somebody who doesn't have the resources that AstraZeneca has, this is our way of giving back to that scientific community so that people, independent researchers, can leverage the data that we have. And this is just one example of that. All right, so that's what I had to cover today. Thank you again for attending. You know, from our point of view, working with AWS is not just about what technology can AWS provide, but it's really, as much of that, it is also about the people that we work with at AWS. They have there's a group that has a lot of knowledge in healthcare, and I think in the HPC world, AWS has the role experts. So I just wanted to say in closing that it's not just about the technology, it's about the people that we've been able to work with, and we really look forward to working with AWS in the future. I mean, this is a long journey, and look forward to working with them in the future to impact people, society, and the planet. Thank you.
All right. Thank you, Sean. So You've seen in the last 40 minutes or so how customers like ARM and AstraZeneca and thousands of others are able to use our HPC and accelerated computing services on AWS and accelerate their innovation, providing business value to their end customers. One of the key aspects for our customers to be so successful in running their advanced computing and HPC workloads on AWS is really the ecosystem of our partners as well as customers, right? So here you can see again a very small subset of our independent software vendors, our ISV partners, as well as our consulting partners. It's very, very important for us to work with these partners very closely in ensuring that their applications provide the best price performance on AWS. Earlier, you have seen a set of EC2 instances that I've talked about, but when it comes to launching these types of new services, our team works very closely with all these partners and making sure that their applications provide the best price performance for our customers. Similarly, with the SI partners, we work with them very closely so they can actually go deploy these services to you all successfully. And in summary, all of our innovations over the past many years have been recognized again at the recent supercomputing conference 2 weeks ago in Denver. So for the 6th year in a row, AWS has been chosen by our customers as the best HPC cloud platform for running all your HPC workloads. With that, I thank you all for taking time on a Monday morning at 8:30 and coming here all the way to the other end of the strip. So really appreciate your time and thank you all.